Okay. Now, this small dot is probably not visible to you, maybe, but generally it represents the derivative. So derivative, if you replace t by n of t, this is what we did in the class or before the midterm. So when you are going from the time domain t to discrete, it's t is replaced by nt. Similarly, instead of derivative, in the n domain, we have difference. So it's the difference of the current value minus difference of the previous value. So this is actually, if you take t common, it's n minus 1 divided by t, which is the difference between two instances, which is equivalent to d of t. Now, let's see if we take the Z transform both sides, what's going to happen, right? So this is just a rearrangement of the same expression. If we take the Z transform of both sides, so Z transform of this derivative is equivalent to Z transform of y of n of t, which is y of z, minus Z transform of z minus 1, because you know when any signal or any system is delayed by minus 1, it is equivalent to multiplication by z power minus 1 in z domain. So we take the Z transform of this one, and t is still there because t is constant with respect to z. And after rearrangement, we end up with a relationship like this. So this is actually saying that if you have derivative dy by dt on this side, and if you have equivalent differentiation in discrete domain, the relationship is such that this s is actually equivalent to 1 minus z power minus 1 divided by t. So from this we can have this relationship. This is where it actually came from. So this is Euler approximation, where s, if you replace s by 1 minus z power minus 1 divided by t, the system is actually transformed to Z domain. The filter is transformed to Z domain. We can't do this with FIR filter because FIR filter are feed forward filter, and we are discussing the feedback filters. So if you have any of the expression in S domain for any filter, and you want to transfer it into a digital equivalent digital filter, so all you have to do is that replace s by 1 minus z power minus 1 divided by t, and you will get the transfer function of a digital filter. Okay, is it wide? Is it loud and clear?
Yes, sir.
Yes, sir.
Easier. You guys,
जी सर ये कंटिन्यूस डिस्क्रीट के केस में इस तरह
नहीं
होगा।
देखें, आपके पास एनालॉग फिल्टर आप लोग ऑलरेडी पढ़ चुके हैं, एनालॉग फिल्टर के एक्सप्रेशंस आपके पास है, ठीक है ना, नेट पे भी अवेलेबल है। अगर आपने कोई एनालॉग फिल्टर का इक्विवेलेंट डिजिटल फिल्टर डिजाइन करना है, तो यू जस्ट हैव टू रिप्लेस एस बाय दिस वैल्यू एंड यू गेट इट्स ट्रांसफर फंक्शन। Isn't that amazing?
Yes sir, सही।
ठीक है, but this is one method of doing it, right? And it has some disadvantage which we are going to discuss in a while. Okay, so we'll just do a small example on it. If you have a transfer function of a system, this is, if you remember, this was the first order filter, right? And if you want to convert it into an equivalent digital filter, you have to specify the sampling frequency. In this case, let's say it's 5 Hertz. So using Euler transformation, what we have to do is that we replace s by this value, 1 minus z power minus 1 divided by t. So this is exactly what 1 minus z power minus 1 divided by t. T is equal to 1 over fs, which is 5. So 1 over 5 is 0.2. So you get this value, right? Plus 1. And after rearrangement, you get this expression, which is a transfer function, which you can further rearrange to get the difference equation, which comes out to be like this, right? If you want to draw them in the S plane or in Z plane, you know how to do it, because see, the pole is at S is equal to -1, which is here in case of S domain, right? There is no 0, so you don't have to plot it. Similarly, in this case, your 0 is at Z equal to 0, and your pole is at Z equal to 0.833, which is lesser than 1, so the system is still stable. Is it clear? Hello?
Yes, sir.
See, it's very simple. See, you have transfer function in S domain. and you replace it by using this formula by 1 minus z power minus 1 divided by t, and you end up with an expression in transfer function. And you guys know how to rearrange it to transform it into difference equation. This is what you have done before the midterm. Remember how to transform
sir.
any transfer function into equivalent difference equation. And you can also plot it as well in the form of poles and zeros.